In this video, I give more examples where Poincare inequality holds or fails to illustrate the point that the existence of Poincare inequalities with smaller p corresponds to the space having more connectivity, having a lot more rectifiable curves. Recall that on a metric space X with the distance function d and a Borel measure mu, having a p-Poincare inequality means that for a large collection of functions and some notion of derivative on them, we have the universal inequality where the derivatives p integral basically controls the average oscillations of the function u. This is also sometimes called 1p Poincare because there is the integration to power 1. It could be also a different constant, therefore there could be also q Poincare. We've seen that or mentioned that Euclidean spaces do support the best Poincare that is out there, which is 1 Poincare. In particular, nice subsets of them, for example, a nice square, the interior of this, will support actually a 1 Poincare inequality, and that's the end of the story. I mentioned also that if you have similar space, but then you pinch it in the middle, you crush this central line segment to one point. This weakens the Poincare inequality to p strictly bigger than 2. So for 2 or smaller, there is no p Poincare on the space. And the reason being that you can concentrate a function, a Lipschitz function, say, to have its gradient only happening here. So you start with basically constant value 0 here. You end up with basically constant value function 1 up there. And the increase from 0 to 1 happens only on this small cone part, double cone part, where because of the smaller area, this side is too small to control this within a universal bound, because you can make it even worse happen. You can have it happen on an epsilon span of distance. Okay, so this is a space that is really well connected between any 2 points. There is lots of rectifiable curves connecting them. I call them onions. Here you pick your x here and your y here. There isn't that many, so this can be made precise in sense of modulus, which we will see again. So all the paths are forced to go through that single point, and that just kills their span. So to make this example worse, one can do the following. So if I have, so basically working with triangles is no different than if I had 2 squares connecting at one vertex, same would hold. So you would have p bigger than 2. And if you have 3 or 4 of these, again, p bigger than 2 is still there. Maybe each time you have this pinching, the constant c goes up a little bit, but it doesn't go to infinity. So still you have p bigger than 2. But what Pekka, Koskela, and Paul MacManus did was to do this infinitely often. So, and the construction is very, very explicit and geometric. So you take your interval 0, 1, and then you proceed with the usual construction of the Cantor set. So you want to remain with lambda length. So you put a length of lambda half here, lambda half on this side, symmetric, and you remove a length of 1 minus delta from the middle. So imagine you are constructing the usual Cantor set with factor lambda instead of being 1/3. So let me clean up a little bit room here. And then, of course, next step would be you will do the same. So you will have this from here to here and this from here to here remaining and the middle removed. So let me also do it on this side. So between here will be remaining, and then this big one, I'm trying to go with lambda quite small, so that the removed is large, the remaining are the remaining subintervals are large, but the removed ones are big. And then what they did say, so the counter set is uncountable, but the complement is made up of, so you pick lambda between 0 and 1, construct the counter set the usual way, C lambda. You must know, if you're following this channel, by self-similarity of this construction and some of the nicest techniques we had when covering geometry of sets, that the Hausdorff dimension, the dimension of this C lambda is log 2, which corresponds to 2 remaining every time, and then log of 2 over lambda. You can see that if lambda goes to 1, then the dimension of C lambda almost becomes 1, so that agrees with the fact that the counter set will be large. And if lambda goes towards 0, then this converges to 0, corresponding to very small counter sets. So that's a double check. Okay, so the complement of C lambda is countable union of intervals. And what Pekka and MacManus did was, for each of those intervals that are removed, you place a square on top, with that removed segment being its diagonal, which doesn't seem like to be working. Here, what happened? Wait a second. Okay, so I'm having difficulty drawing squares. So you have this, and this is the whole thing, including the interior, also the boundary. It's a closed diamond. And then, of course, we repeat it with every one. So next level, you have removed this, and then this, and similarly. So you will have 2 of them, and in the next step, there will be tiny ones removed from between here, and there will be 2 to power 2, 4 of them, and then you repeat this construction forever. So this way, you will have what is called a counter diamond. So it's a countable number of diamonds on this 0, 1, and there's also the closure of them. So some points are limits of these diamonds. The counterpoints, indeed, will not be contained in, not all counterpoints will be contained in as the boundary of a diamond, but all of them will be limits of some sequence of diamonds. So this is, again, an infinite version of this pinching. And every time you come to this, let's say, bottleneck, your Poincare constant, well, one of them is enough to push you above 2, but what will be the effect of the accumulation of all these pinchings? So what MacManus and Koskela prove, so I will show you the paper at the end. So this is Koskela and MacManus from 98, is that this space with the inherited Euclidean distance, and with the Lebesgue measure restricted to it, supports a P-Poincare inequality for all P strictly bigger than 2 minus dimension of this C lambda divided by 1 minus dimension of C lambda, which is some P0 bigger than 2. So with one pinching, we had that we have Poincare bigger than 2. But now we see that it's even worse. So you have to be actually bigger than some number, which itself is bigger than 2 strictly, and not for any P smaller than that. So we see that the accumulation of this extra pinchings, infinitely many, makes the best P Poincare exponent P to be even larger, which in general means worse or weaker Poincare inequalities. If you look at this, you see that if dimension of C lambda goes to 0, you go back almost to the same constant of 2. So if dimension goes to 0, then you are back to almost pinching just once. And that explains because then with very small Cantor set, you have very large diamonds mostly, and the negative effect from the pinchings goes down. However, if dimension of C lambda is close to 1, then this is actually blowing up to infinity because the denominator almost becomes 0, so that you will have worse and worse Poincare inequality if the dimension is large. In that case, the pinchings happen more often at large scales compared to when dimension is nearly 0. Okay, so the message here being that more pinchings, loss of rectifiable pencil of curves means a weaker Poincare inequality. In the next video, we will see the opposite effect. So we will begin with this and modify it to add more connectivity, but not as large as getting back to this square. So somewhere between this and this. And if you're interested in seeing that one, keep watching the videos and see you in the next one. Thank you so much.